This is the video lesson for Coulomb's law. The learning target for this lesson is, I am learning to calculate the force on objects due to electric charges by using Coulomb's law. The success criteria for this lesson are, I can recognize the equation for Coulomb's law and understand what the variables mean. I can use the correct units for electric force and charge, and I can calculate the force between objects due to electric charges on the objects. So what is Coulomb's law? So here we have the equation F is equal to K times Q1 times Q2 over D squared. So what are all these variables stand for? So F is equal to the force due to the charges on the interacting objects. So K is the Coulomb's law constant. So this is Coulomb's law constant, and this value is 9.0 times 10 to the 9th, and then the units are newtons meters squared per coulomb squared. So that's the units for the constant there. Q1 is the charge on object 1, and that's in coulombs. Q2 is the charge on object 2, also in coulombs. And then D is the distance between the centers of the objects, and that is D squared. So the distance squared, the distance between the center of the objects. Okay, so if you notice, this equation looks very similar to the equation for the gravitational force, which is F sub G is equal to G times mass 1 times mass 2 divided by the distance squared. So here, instead of masses, we have our charges squared, or our charges times each other divided by distance squared, and then we have this force constant. So for gravity, we have G, which is the force constant, times masses times each other divided by distance squared. So Coulomb's law is very similar to that. So we have our two objects, the charges on the two objects divided by distance squared, and then we have our force constant. Now the force constant in Coulomb's law is much stronger, much stronger than the gravitational constant. So 9 times 10 to the 9th is way stronger than the gravitational force constant. All right, so remember that force is a vector. So force is a vector, which means that it has directions. So when you draw a force vector, you're going to have arrows which point in the direction of the force. So for an attractive force, so when you have objects that have one has a positive charge and the other has a negative charge, the arrows are going to point towards the charged objects. So if we look at an example here, we have a positive object and a negative object, positively charged and negatively charged objects. The vector arrows point in the direction of the objects. So here we have this arrow pointing towards from the positive object is pointing towards the negatively charged object, and the arrow from the negatively charged object is pointing towards the positively charged object. So for repulsive forces, the arrow points away from the charged objects. So here's another example. We have the repulsive force. So here we have two positively charged objects. And so the arrow for the force vector points opposite. It points away from the charged objects. All right, so let's take a minute to look at the units for charged particles and the force the force due to charged particles. So the units for Q1, and Q2 are going to be coulombs. So it might not be a full coulomb, it might be a microcoulomb or a nanocoulomb, depending on how much the charge is. So a microcoulomb is 10 to the minus 6 coulombs. A nanocoulomb is 10 to the minus 9 coulombs. So we rarely ever see a full coulomb because that's a lot of charge. K has the units newtons times meters squared per coulomb squared. So you can see here if coulombs are, or if the charges Q have units coulombs, so we have coulomb times coulombs, that's coulomb squared, and then we have D squared, and D is going to be measured in meters, so that's meters squared. So we have C squared over meter squared. So if we look at the units for K, we have newtons times meters squared per coulomb squared. So our meters here divide out and our coulomb squared divide out, and we're left with newtons, which is the unit for force. So newtons are the unit for our electric force. So unit for force for electric force. So all forces have the units newtons, including electric force. All right, let's look at some examples on how we use the Coulomb's law equation to solve some problems. So example number 1, we're going to calculate the force. So a charge of minus 2.0 times 10 to the minus 4 coulombs and a charge of 8.0 times 10 to the minus 4 coulombs are separated by 0.03 meters. What is the force between the two charges? All right, so we're looking for force here. So we can say Q1 is equal to 2.0 times 10 to the minus 4 coulombs. Q2 is 8.0 times 10 to the minus 4 coulombs. And then our distance is 0.30 meters. And we're looking for our force. Force equals question mark. Okay, so our force equation is equal to 9.0 times 10 to the 9th. And that's going to be times Q1. So we don't have to worry about the signs on the charges when we're calculating the force. It doesn't really matter necessarily. We can just kind of ignore the sign. That's coulombs there. And then divide all of that by our distance, which is 0.3, and we square that. So our force is going to be 16,000 newtons. So a lot of force between those two particles. And since one of these particles is negative and one of them is positive, the force between them is it's an attractive force. So the force arrows are pointing towards each other. So the force vectors are pointing towards the two particles. Okay, in this second example, we're calculating the charges on an object. So we have two vinyl balloons with identical charge are given a separation distance of 55.8 centimeters. The balloons experience a repulsive force of 2.717 times 10 to the minus 3 newtons. We want to determine the magnitude of charge on an individual balloon. Okay, so our distance is 55.8 centimeters, so we want to put that into meters, so we're going to divide by 100. So we move the decimal place over 2 to the left, so that's 0.558 meters. Our force between the two charges are 2.17 times 10 to the minus 3 newtons, and we're trying to figure out Q1 and Q2. So they have identical charges, so they each have the same charge. So our equation up here, Q1 times Q2 equals F times D squared over K. So this is just a rearrangement of the force equation. So we have Q1 times Q2 is equal to our force, which is 2.17 times 10 to the minus 3 times our distance, which is 0.558. We're going to square that, divided by k, which is 9 times 10 to the 9th. And that's going to give us our Q1 times Q2. Okay, so the charges together, so Q1 times Q2 equals 7.51 times 10 to the minus 14. So to get one charge by itself, we're going to take the square root of this number. So Q1, we'll say, is equal to the square root of 7.51 times 10 to the minus 14. And the reason we're taking the square root is because these two charges are identical. So we could just say that Q1 times Q1 is equal to this number. So Q1 is equal to the square root of this number, which is equal to 2.74 times 10 to the minus 7, and these are in coulombs. All right, in this last example, example number 3, we're going to calculate the distance between charged objects. So we have our distance formula here, which is the square root of k times q1 times q2 over f. So again, just rearranging that original force formula. So we have two charged objects having charges of plus 7.17 times 10 to the minus 6 and minus 3.17 times 10 to the minus 6. These are in coulombs. Attract each other with 0.559 newtons of force. We want to know what is the separation distance of the two objects. Okay, so our two charges, we have Q1 is equal to 7.17 times 10 to the minus 6. Q2 is equal to minus 3.17 times 10 to the minus 6. And then our force is equal to 0.559 newtons. So we're looking for D. D equals question mark. Okay, so we have D then is equal to the square root of K, which is 9 times 10 to the 9th. Multiply that by Q1, which is 7.17 times 10 to the minus 6 times 3.17 times 10 to the minus 6. And again, you don't need to worry about the signs when you're calculating the force or the distance. We only need to know that the force vectors are pointing towards each other, because these are one's negative and one's positive, so they're attracting each other. And then over the force, which is 0.559. So our distance then is going to equal 0.605 meters. So that's equal to 60.5 centimeters. So the force so the separation between these two objects is 60.5 centimeters between their centers. So we have, assuming, let's say there are two balloons, the distance between the centers of the two balloons is that distance D. All right, everybody, keep asking questions. It's how you learn new things.